Everyone. Oh, perfect. My name is Andreas Freund. I work for Enterprise DB. I actually started like very short time ago. So a lot of the content that I worked on in these slides were done while I was working at Citus Data. I'll tell that at the point just to make it fair to sign who allowed me to work on these things at the right moment. I'm also still have an advisorship position at Citus Data. But what I want to talk today about is how can we make Postgres more efficient? And what does efficient actually mean? It means how much work can you do with a certain amount of resources. For example, with a CPU clock assignment, how much of a query can you process with one CPU? If you make things more efficient, what that would mean is that you would need less CPU, for example, or you need less memory for the same amount of work. Or you can, in the contrast, increase the amount of work, but keep the time or something at the same. And I think that's something that Postgres, for some workloads, has been not that great at. That is, we have used too much CPU for certain tasks just because nobody focused a lot on improving it, because we were worried for a long time more about scalability, that is, the ability to run a lot of things at the same time, the ability to possibly start like using multiple machines, the ability to use parallel query, that is a single query that can use multiple CPU cores. All of these are super important things. I think just that while working on those, we've disregarded a bit that we actually need to use each of these cores more efficiently. And I think the main problem around efficiency that Postgres has is not about memory. There's a lot of memory optimizations that we could do, like the amount of memory used. It's about how much CPU we need, CPU time we need to complete queries. And what I want to talk about today mostly is analytics type queries. So not queries where you have a lot of very short not of workloads where you have a lot of very short queries, like typical transactional workloads, like a typical web app. That's not really what I want to talk about, because I think actually Postgres is pretty good for those kinds of workloads. So I don't feel the need to focus on that right now. I think we don't need to improve as much there to be competitive with other databases. In fact, there's a lot of cases where we are as good or even better than some well-known other databases in transactional workloads. There's some issues there too, but in general, we're pretty good. But for analytics type queries, that's not necessarily the case. There's a lot of queries where we need a lot more time to answer them than some competitor products. And I think one of the reasons that it didn't used to be as big of a problem is that most people were using Postgres for transactional workloads, and now the share of people that want to do analytics with Postgres increases. Does everyone know what analytics type queries are? If not, okay, cool. Then I don't need to go over that. Yeah, and so I think that's a big field that Postgres could be used more in if we were better at it. So, and one of the big improvements that has been made there in the last, in the 9.6 release and now in the 10 release is parallel query, which means that we can use more than one core for query processing, but that actually only helps you if you have available cores. And the number of cores in a system is limited, and especially if you have to run multiple queries at the same time, there's also not that many cores you want to give to a single query triggered by user, because otherwise you're running out of resources pretty fast, or you have to buy massive amounts of machines or VMs or whatever to be able to run queries fast enough. So even if you have parallelism, that goes beyond a single node, where you have, for example, some distributed layer on top of Postgres, for example, Citus or Postgres XL or something like that, even then you are constrained by the amount of work each of the individual nodes can do if you have a analytics-heavy workload. And I think there's generally three rough areas where Postgres that are improvable. there's cases where that's the left column here, where we actually know how to execute a query faster than we currently do, and but we choose the wrong plan. We choose a slower version of the query to execute it, and we should choose a better one. Does everyone know what a query plan is or not? Who does not know what a query plan is? Cool. So that's, I think, a category of things where we can use a lot of effort to better choose the right query plan. And I will go through a bunch of examples where we have made improvements in the past, and then very recent improvements, and then something like where people are working on that hopefully improve things in the future. And I'll occasionally ask whether you hit these types of problems just to get some feedback to know whether you think that's an area we need improvement or whether it's something like where you don't care. The second category is that we sometimes need to be smarter at executing things. That is, we choose the currently fastest query plan, but like in theory, there would be an approach that would make it faster to execute a query. We just don't have our query execution engine doesn't have the capability to do something in an optimized way. And so there the solution can be to add new ways for the execution to be done. At some point, we started with very few things how a query could be optimized, and then for performance reasons, we extended that, and there's no reason to stop there, and we have done so in the not too distant past. And the third category is we actually chose the best possible or a very good way to execute a query, so we haven't chosen the wrong plan. There isn't really a good idea that is practical that could make the query execute faster, but it's still too slow. And I think that's a very important category because both the better plan and the smarter execution type of things are areas where where we can use some more improvement as the Postgres community, but there's plenty of cases where we actually chose the smartest way to execute something. We're still just too slow. So that's something I've focused a lot of energy over the last couple of years, last 1.5 years or something, to make things faster on. And I'll show some of the recent work and then some of the future work that hopefully will get into Postgres 11. And then there's also some less determinate work. Just to go through the examples here, this is a bit on the planning side of things. For example, in 9.2 we added the custom plan logic, which can make a large back then could make a large performance difference. For example, before 9.2, if you had prepared statements and it had parameters somewhere in there, we didn't take them into account for planning. We didn't do any selectivity estimation based on these parameters, which often led to very, very bad plans. We have improved on that. It's better now, but you still very frequently can run into problems. But it's still improved a lot. Another good example, I think, for especially for web, like for automatically generated queries, is that in 9.5 we added join removal, which means that if you have a left join in a query and the columns from that are not actually needed, and the join is guaranteed to only return one row for where you join to, then we can actually just remove the join and don't do it. And that's pretty useful because a lot of these web frameworks that automatically generate queries add joins that you actually don't need, and you can optimize away. Or other cases where that often helps is you have a view that shows a lot of column, but when you select from that view, you don't actually need those columns, and then we can just optimize the join away. Sorry. Then we have multi-column statistics that I'll go into a bit more detail about that. And on the smart execution side, in the past, what we've done, for example, is we have prefetching and index-only scans. I'll explain what these do in a bit. And we have Brin, which is a new index type. And we've previously added other new index types. And that allows you to do scans fast that you previously couldn't do fast. So that's definitely an example of smarter execution because we can use a new index type. And another example that's a bit different is grouping sets. What grouping sets allows you is to do a query and group your result sets by multiple dimensions and get them as one result. And that often allows to avoid processing the data multiple times. Before grouping sets, you had to write the same query and do unions between all the results. And that meant you had to process the data a lot of times. It also added, at the same time, a new SQL level feature. So it's not quite just smarter execution, it's also a new SQL syntax. Existing examples for executing queries faster are, for example, the sortings improvement Peter Gegen did in the last few releases, where if you have an order by and or you have a group by that's implemented using sorting, then that can be a lot faster in the last few releases. I think there's still some potential for further improvements. So that's a good example for why it's very nice to just make things faster, because it's not like in the Brin case, for example, you have to create an index to take advantage of it, whereas in the faster sorting case, all you need to do is upgrade and it automatically gets used. Similar in contrast to grouping sets, that you don't really have to do anything. There you have to use the query, whereas with faster sorting or any of the other faster execution type things, things just get faster without having to do any work. I'll also talk a bit about the better fast performance improvements we made in Postgres 10. Okay, so let's go through a few of the examples of the improvements we made in the past, and it shows examples where I think that people might actually not know about them or how to take advantage of them, because I thought that would be, besides explaining how we can make things faster and where you might be able to help, it will also actually help you possibly to be better, improve your current situation. So one very common problem in for analytics queries is that you have columns that are correlated. For example, if you imagine a query that filters the number of all US citizens by people that live in a specific city, because we're here, say San Francisco, but you don't want the entire city, you also say we want only the zip code 94102, and that's where we currently are. And the way Postgres estimates how many rows are going to be returned by that is it takes the likelihood of, by using stats, of how many people, how many rows in total are of the population are in San Francisco, and then it takes the likelihood of how many people live in the zip code 94102, and then it just multiplies those likelihoods together and assumes that the result, and that's normally if you have two conditions that are not related. That's a reasonable way to estimate how two ANDed together conditions filter something. But in this case, cities and zip codes are very well correlated, because most zip codes are exactly in one city, and most cities consist out of multiple zip codes. So that's not very good, because what happens in this example, for example, when you take the likelihood of something in San Francisco is roughly 1 in 3 divided by 348, because that's roughly the population of San Francisco, the citizen population, because I only had data about US citizens, which I'm not, but okay. So that's the likelihood of roughly for its population from the US. And then you have a filter that says, okay, the zip code filter says there's about 30,000 people here. So that gives a likelihood. And if you don't have, if you just do the way Postgres does the likelihood, the selectivity estimation, it just multiplies those two. And then if you take the total number of rows, and you get 90 people. And there's actually 30,000 people living here, because the filter city equals San Francisco doesn't actually filter out any rows. So what happens is that the query planner assumes there's only 90 rows, and even though there's 30,000 rows. So we are wrong by roughly 3 orders of magnitude. And quite often, if you have an order of magnitude or more in the misestimation about how many rows are going to be returned, the query planner will choose an optimization strategy that makes no sense whatsoever. And if you have more than 2 conditions and that are correlated, you can, I've seen estimations that are wrong by orders of 9 orders of magnitude, which obviously is completely ridiculous. And you don't just have this problem where you have an and in there. You have the same problem with with ors and so on.
Are your slides online or?
Yes, the first slide the last slide will show the URL again.
Oh, okay.
Oh, and I haven't put them. I'll also put them onto the website, like the PG Opens website, like after this talk. So what we have in Postgres 10 now is a very cool feature, which is that you can define a set of columns that are where we compute the likelihood of how are the values correlated between 2 columns. And you can just say create statistics, and you have to give it a name, and then list the columns, like in this code, zip code and city, and then from the table, and then that the next time you do an analyze, or where AutoVacuum executes an analyze, it will compute the correlation statistics. And then afterwards, when you do have a query that filters by both, it will take into account how well correlated those tables are. And then the estimates of that will be a lot better. I haven't actually listed them here, but I think I downloaded this and executed this from some US government data, and afterwards the estimate was like 34,000 or something. So like an error of like 10–15% or something, instead of 3 orders of magnitude. So like it's a lot better. There's a lot of further improvements we can use if you, for example, have inequality comparisons, for example, 2 date ranges, say an order datum and a ship datum in some column, and then you use multi-column statistics. That doesn't actually yet work, but that's much less common, I think. So this actually allows you, but the feature allows you to get a lot better query performance in a number of cases, and it's something that is really, really hard to address if you don't have this feature, because you can, what could you do as an application developer? You could add logic to your application that says, if I filter by zip code and it's not one of the cities where zip codes span multiple cities, then I leave off the city filter. And like, I mean, then the amount of logic you have to add to your application for that that's not good. You don't want that. The database should solve that. You might say, why doesn't the database just compute statistics between all columns in a table? The problem is that like if you want to do one-to-one pairing of correlations in a table, and you have 100 columns in a table, that is a lot of pairings, and the statistics get very expensive. So that's why you have to specify them. A good example for being smarter about execution, I think, is our index-only scans. And that's a feature that was added in Postgres 9.2, I believe. So we wrote a pretty bogus query here, but I just wanted to have an example. We have a query where we select the ship date and count star. So we want the number of items on a single date. And we filter by the date in a range. And we group by the ship date, because otherwise you couldn't do the count star. And then we want the date with the most items shipped on a certain date. If you don't have index-only scans, what will happen is that it does a bitmap scan on the item scale to filter down the range, and then it will go to the table and fetch all those rows from the table and return them. And if the executed time is, I can't read this from this angle, 109 seconds to execute the query, and we access 1 million buffers. That sometimes the buffers are previously accessed multiple times, but still, that's a lot of time. And then if we instead allow index-only scans, that is upgrade to 9.2, and then do some steps I'll explain in a second, both the time and the number of buffers accessed are better by a couple orders of magnitude. So this is why smarter execution, you can have huge savings if you find a new way to execute things quickly. Unfortunately, there is some trickiness to when index-only scans are used in Postgres. The big requirement is that all columns that you want to select have to be in the index. So the index can't return rows that aren't in there, not that surprisingly. And that is not that confusing to most people. But in addition, in Postgres, the table has to be vacuumed regularly to be able to use index-only scans, because only portions of the table that are known to be visible to everyone can be returned by index-only scans. Otherwise, it will still visit the heap, and that makes things slower again. So, and auto-vacuum will do that for update-heavy tables, but unfortunately, it will not do so for tables that are insert-only. So if you have an insert-only table, which a lot of tables are, then you might need to occasionally vacuum them yourself to see this kind of speed up. It also, because of the feature, it often can also make sense to add extra columns to an index just to be able to use index-only scans. I've a number of times created extra indexes that actually added extra columns to an index, which made the index a lot bigger just because it made the overall query execution a lot faster. If somebody has questions, please raise your hands. Yeah?
We run into issue because this kind of we have a transaction, what called transaction, idle in transactions, which stopping the vacuum all the time.
Yes. Unfortunately, if you he was saying that he has idle in transactions that are long running that prevent auto vacuum marking at everything as visible to everyone. Unfortunately, at the moment, that's a restriction you have to live on, and it is useful to set up alerting that says, hey, this transaction has been running long, and you cancel it. Postgres, I think it's either 9.6 or 10, has a feature where you can say there's a timeout for idle transactions. I worked on that, but I forgot when that was. Another example of a smarter execution strategy that actually not a lot of people know about is that Postgres these days can use prefetching on I/O. And this only matters, obviously, and it prefetches rows from the disk. So it only matters if you have workloads where not all of your data is in memory. But for those, it can actually help a lot. It was written in 8.4, I believe, and in a time where nobody had SSDs. And for rotational disk, the benefits are pretty large, but not huge. And for SSDs, the benefits can be really, really huge. So what we have here is a very similar query to the one before, except that we have the same index, but we don't do a count star. Instead, we sum up the quantity, for example. The difference is that the quantity is not in the index, so we can't use an index-only scan. So instead, we again have to access the table itself. And if you execute that query normally, then it takes 30 seconds on my laptop for a laptop very, very good SSD. And this is on the data set for TPCH scale 10, but it doesn't really matter. It's just an example. And my SSD, in the normal case here, is able to return data at 260 megabytes a second. It does about 100,000 I/O ops a second. So this is pretty fast. But you can see that the utilization is only 60%. So the disks itself says, hey, I could do more. But because all the I/O requests are done when the heap scan happens, hey, I need this block. Then I process that block. Hey, I need this block. I process that block. That means during the time that the block is processed, we don't do I/O, and during the time that SSDs can do multiple I/O requests in parallel. In fact, most SSDs can do between 128 and 512 I/O requests in parallel. And if you do just reads individual blocks, then the disk can't benefit from that. So what you can do is you can turn on effective I/O concurrency. And for that, at the moment, only has an effect for bitmap index scans. But for those, what it means is that it will go whenever it has to access the heap. It will fetch the next n block, whatever settings you set it to, and then it will fetch that many blocks ahead and tell the operating system, hey, please read this block. And then we will have the data available at the time that the query execution actually gets to that data. And for example, if you set it to 512 on my disk, then you get like roughly double the speed, and you can also see that the I/O throughput is roughly the double. But that's with an SSD on my laptop. If you do the same query on an Amazon EC2 instance, where you have SSDs but over EBS, the biggest benefits I've seen is 120 times as fast as before, because there the latency to access data is much higher. So the penalty for doing everything sequentially that instead of in parallel is a lot higher. So like tuning the effective I/O concurrency, if you have SSD disks, can be quite remarkable. Now,
What version was the feature you just
8.4. So yes, 8.4. So every supported version has that. So you should be fine. If you use something older, you have bigger problems than performance. If you have used something older than that old, really, really, please upgrade. We don't do any security fixes. We don't do any data corruption fixes for versions that old. So yes. But what if you have a query where your execution, where your plan is the best, and it's still too slow? Then we come into the faster, that we need to make existing query plans faster. And here I'm talking about an improvement that is made in Postgres 10, and that I spent a lot of time on. Most of the time was spent while employed at Citus Data, and they allowed me to contribute this as open source, so thanks for that. And what we have here is the TPCH query 1. And it's a pretty simple query. We essentially have just one table, and there we filter a range of dates. And as you can see by the year ranges here, the benchmark is really, really old for like in computing ages. And then it just groups by 2 columns and orders by those. And for those groups, it computes a lot of aggregates. So what you can assume that is that if you have that range is a large enough portion of your data, you're going to get a sequential scan. If it's a smaller portion, you're going to get a bitmap index scan that scans this. And then you have a lot of aggregates, and the computation of these aggregates is probably going to take a lot of time. So what the query plan that I'm talking at the moment about is that where it exactly takes a sequential scan, and it filters by that date range, and then you have a hash aggregate, and a hash aggregate basically just means that it's all in memory, and that groups by these 2 columns, and there's only like relatively, because there's only very few of these flags, there's actually only going to be very few output rows. And then it computes during that all these aggregates that we saw in the previous slide. So the question is, looks like a very reasonable plan for this. You could replace a sequential scan with a bitmap index scan, depending on the amount of data, but the results aren't going to change very much. So what can we do to make things faster? We have 2 things here where a lot of time is spent, or 3. We have the evaluation of the filter, where it filters this. And Postgres has a so-called expression processing engine, and that evaluates that gets input, like for example, the ship date and the constant here, and knowledge that it has to evaluate the smaller equals operator, and then it evaluates whether that's true. And that engine was basically written, hasn't been rewritten since Postgres was added the SQL feature. So it's basically the same forever. So we can make this faster. That also helps with a lot of these arguments, because the arguments to the aggregate functions here, extended price or then the math here, all those are also expressions that have to be evaluated. So there's a lot of expression processing here that we can make faster. Then there's also that we have this hash aggregate. What that means is that we have a hash table that says, we have the key to the hash table is basically the return flag and line status values. And then we have on the value side of that hash table, we have the current aggregate transition values. So, for example, a running counter that says what's the current sum for the existing quantities that we've processed so far. So what you can do is we can make the hash aggregate faster, we can make expression processing faster, and then some other smaller tricks. FastX.
Yeah, I have a question. Why are you even doing a hash aggregate as opposed to just an aggregate when you've done the sort?
There's no sorting here on the bottom. The query processing starts at the innermost side. Look, we start with a sequential scan, and then we do the hash aggregate, and then we sort the result. The sort is only of the 6 resulting rows. So what we did, and I worked primarily on that, is we rewrote the way the expression evaluation works. We rewrote the way that aggregates, the arguments to aggregates are done. Instead of doing them one by one by one by one, we invoke the expression engine for each of the arguments separately. And now we do all of them at once. And we replaced the hash table implementation that underlies the hash aggregate with a new one to make things faster. So the performance effects of that are, like here we see the TPC-HQ1 query, and we see the different versions. So I have numbers starting from Postgres 9.4, 9.5, 9.6, and 10. And you can see that we actually went slower from 9.4 to 9.5. And that turns out to be because of the grouping sets feature. And that's one of the interesting problems here, is that often enough, if you add features that make some things faster, for example, if you have a query with grouping sets, it makes also the complexity added makes other things slower. So that's a lot of the trade-offs here, is that you have to deal with like contradicting goals. So we saw some slowdown here, and then we can see that in 9.6 we already went a bit faster again, and then we see the results of the rewrite of both the expression evaluation engine and the hash table changes. That's a pretty good saving. I think it's like roughly 35% faster. And since 9.6, we also have parallelism, and this one is a query that can very easily be parallelized. So we can also, my computer has 4 physical cores and 8 threads, but so I did just to show that at the same time with 4 cores, we can see that the numbers are a good chunk better, but we see a similar, like percentage-wise, we see a similar improvement if we use parallelism. Yes, you can set max parallel workers per gather. One of the more intuitively named settings that will determine how many cores are available. In 9.6, it's off by default. In 10, I think the default is 2. Max parallel workers per gather. There's different places where you can use parallelism, and so that's why it's per XXX, but it's not exactly the most intuitive naming. There's a couple settings. There's also one that, yeah, if you want to see the settings for parallelism, it's more time than I have here, sorry. So, okay, these are like the state till Postgres 10, which is going to be released in a few days, weeks. So I now want to talk a bit about the future. We just saw that the same query that we just looked at before still wasn't super fast. I mean, it still didn't run like, there still seems to be some optimization potential. And if you compare it with other database products, you can see that some other people can execute it still a lot faster. So I wasn't quite happy enough with these results. And but at that point, using some we still spent a lot of time doing this, evaluating these expressions. So what if the normal solution, if you have an interpreted language, and that's essentially what SQL and our expression evaluation all is, to make things faster, is to say we want to compile this down to native code. Similarly, like how JavaScript in the browser is just in time compiled to native code, or how languages like Python are a lot slower than compiled languages like C or even now Go and Rust and whatnot. or Java. So the idea is to make things that are executed a lot of time and compile them down to native code instead of interpreting them. Now, one has to be aware that compiling things down to native code actually takes time and effort, because you have to make transformations, you have to then tell the operating system this memory is executable, and so on. That is a significant overhead. So this is not going to be beneficial for queries that run like 3 milliseconds, because you're going to spend like 5 milliseconds doing the optimization work. So it doesn't make sense for those. But for queries that take a few hundred milliseconds to a couple seconds to hours, then a lot more work can be put in, and if you put in for a query that runs an hour and you put in at the beginning 50 milliseconds for just-in-time compilation and saves you 50% of gives you 50% faster query execution, you're not going to notice the slight slowdown at the beginning. So what we were able to do is that, and that's a patch that has been submitted to Postgres, but is not yet integrated into Postgres, is that this filter gets compiled to a native code, and then what that means is normally what happens is that we have one function call that extracts the value for the ship date column, and then one that it represents the constant, and then we call a function that's called, for example, date underscore less or equal. And that function call is you can add new ones of these. That's what the Postgres extensibility allows you to add new data types. It allows you to add new operators for everything. But all this flexibility also means we have to call a lot of functions that implement these operators and data types. So what the JIT does is both it compiles all this into one function, but it also inlines the operator that implements the date.le thing. And the same is true for all the aggregate transition values. And so I implemented that and worked on it a lot, and I think the performance results show that this is a very convincing way to go to. So we have the same graph as before. I chopped off the 9.4 part just because I thought it doesn't contribute much here. So we can see that this is Postgres 10. We can see the noticeable improvement here. And then there you can see Postgres 11 as of currently commit, like the current state, and the development of the 11 branch only opened a couple of weeks ago. So that's why there's basically no difference. That's to be expected. And then there's here in between, this one is basically my development branch, but with just-in-time compilation disabled. And it turns out to make just-in-time compilation usable, I had to make independent improvements. And those independent improvements actually made things faster themselves. So that's always a nice result, because that type of improvement also helps queries where it's not worthwhile to do just-in-time compilation. And then with just-in-time compilation, we can see that the total amount of time here is, again, quite drastically reduced. So between 9.6 and 9.5, we basically reduced the runtime for this type of query by 3x. I think that's pretty good, and I think we can do that for a lot of type of queries. I just took tpch query 1 here as an example because I didn't want to run a lot of queries, and because it has a decent optimization potential. There's other tpch queries where you actually see bigger benefits, but they're super long, and so they're a bit awkward to show. And there's a lot of other queries where, with the current just-in-time compilation implementation, you see very small benefits because the timing is not in the function evaluation, and that's what I improved with this. We can do the just-in-time compilation for a lot of other things. Here, the results here are not just the expression evaluation; they are also the conversion from when you read something from a table, the format on the disk, or in shared buffers, of how a tuple is laid out, and an efficient in-memory representation are not the same, because the priority when you have something on disk is to have it relatively small, whereas the priority in memory is to be able to access it fast. And so we have a different representation for in-memory and on disk, and the conversion between those two is also relatively slow. So that's was something else that I made faster with just-in-time compilation. So I think I really hope that this work can get into Postgres 11, and we'll continue to work on it, and I think it has a pretty decent chance. So now it's going to get a bit further out. I think it's all stuff that might happen in the Postgres 11, Postgres 12 timeframe, but there's no finished patches, so it gets a bit more speculative.
Is there a date for that then?
Like usually it's once a year, so it's like just in a year. I mean, we have in the past had some releases that were a bit delayed, but the hope is that we can release within a couple days of last year's release again. So we had one example of a future make execution faster using the same query plan. So an example, another thing what we want to do is we want to make execution faster smarter in the future. And here I have an example of how a join works currently. If you have just what we have here is a join between two tables. We have a where clause that says on the orders table there is a date where we restrict by date, and then we have a nested loop join that joins that to another table, and that table is in this case shipments. So what we can expect here is that a lot of orders are going to be batched together in shipments, so there's going to be fewer shipments than orders. And there's different ways to execute this query. Because we only have a filter on the orders table, we have to start basically with filtering the orders table by the date restriction. It might if we had an index, this might also be a bitmap index scan or an index scan, but it doesn't really matter. And the way nested loop join works, it gets one row from here and then goes into the join code, and the join code then goes to the index, does an index scan on the shipment table, and it just now computes a restriction based on the shipment ID from the row that we got back from here. And then it does an index scan and returns that. And then we do the same for the next row, the same for the next row, the same for the next row, and the same for the next row. So what happens is that we have to do as many index scans on the shipments table as we return rows from the orders table. And that's, if you return 5 rows, that's perfect, because it's very quick to do 5 index scans. If you return 500 million rows, 500 million index scans are going to take a lot of time, because every time, if your workload doesn't fit into memory, you have random I/O on every single index scan. If you don't, you have still like relatively complex accesses within the index scan that take time. So Postgres has another execution strategy for this, which is a hash join. The way that works is that instead of going to the underlying table for every row, what we do is we build a hash table over all of the data in the shipments table. So what happens is that we read all the rows in the shipments table, and then we have a hash table that says, based on the shipment ID, return me the row that is in the shipments table. And because we now don't do an index scan for every time, it's going to be a lot faster. But the penalty for that is that we have to fit the shipments table into memory. We have ways to to avoid having to do all of it in memory, but yeah, which means it's going to take at least as long as it has to take to scan all of this. But what if you're a big company and you have 500 million shipments or something? Then this is not a viable strategy, because you would have to load all of this in memory. That might be okay for your yearly reporting job, but it's not okay for like something that has to run within a few milliseconds or a few seconds. So what we can do is we can try to combine those two execution strategies. We can do something like this. We have this new type of join. I named that cached nested loop join, where we again get one row here. From the nested loop join, instead of going to the index scan, we first check some cache that has a specific number of rows, which we have indexed again by the shipment ID. We check whether it's present or whether it does not exist in that table. And if only when that's not the case, then we visit the underlying table. You might say, but that's not going to save me anything if all the shipment IDs are different, because then the cache will never be hit. So this is not useful for workloads or for queries where you have where every value is different. But quite commonly, you will have, for example, multiple orders for one shipment. So if you have, like, for example, 100 orders per shipment, then it can be very useful to reduce the number of accesses to the underlying table by a factor of 100. And quite often you have, like, even higher cardinalities. I have a very rough prototype, and the results like basically are as better as a hash join by the factor, as a nested loop join by the factor of how many repeated values you have. And that seems to be working pretty well. It's very, very rough, so I doubt I can get that into version 11. Yeah, but the lateral join is implemented as a nested loop join. Yeah.
So what's the difference? Because I could also write an inline lookup.
Let's do that afterwards, because I have one last slide, and otherwise I might not go through it. Like, please come up and we talk afterwards about it, okay? So, and I think there's one other case where we currently often select the wrong plan, and that's, in my opinion, the worst one of those is CTEs. If you have a CTE, who doesn't know what a CTE is? Okay. A CTE is basically a named query. We have, for example, here we have the per day query, which just groups everything by date. And then this one, the per day, you can now select in the same query form. So what we do here per day, then we can select star from per day, and then that basically means the results of this, and then you can select from that. Quite often you can use that to make your query simpler and to avoid repetitive work, because the way it works in Postgres is that if you have scanned this once, it will cache that in memory, and so you won't have to scan it, build the query again, which can save time if it's like an expensive query. But in this case, what we have here, we select only for a single day, and then union that with it for another day. But how do you think this will be executed in Postgres? Yeah, it does the entire CTE. It scans the whole table, like for every single day, like for all the data ever inserted into the database, and then afterwards it filters those by the date. Whereas the much, much smarter implementation would be to say, hey, I'm going to execute the content of the CTE once for one day and once for another day, and you're going to only look at 2 dates. And if you have like 5 years worth of data and you only access the data for 2 days, that's going to be a lot faster, obviously. Just on 1 year's worth of data, on a couple years worth of data, you can easily see that our current strategy is not perfect. And I think that's something that we really, really need to work on, because CTEs are more and more used in analytics queries, and we're pretty bad at it. Okay, I think that's it, and I have about 2 minutes. I think it would generally be based on selectivity, and like we have cardinality statistics that say how often like our values repeated, and that would also take into account the multi-column statistics. Yes.
On the multi-column statistics, are you storing what's the equivalent of most common values there, or is it purely multi-dimensional histogram?
Good question. I can't answer. It's a bit more complicated than that, because you like but I can't answer the question in like to the full extent. I looked at the patch like a couple years back, and I don't remember that amount. I think it's both, but I'm not 100% sure. Okay, one last question if somebody has one. CTE is within a single query. So like a materialized view is a database object that will exist forever, like until you drop it again, or if it's like a temporary table, then until the end of the session, whereas the CTE is within a single query. So it's not a persistent object in any way. Okay. That's it.